Thanks for the likes. If you have me a negative, that's already 2. That means you watch by video. For this, I'm thankful. If you gave me a like, means you watch it and liked it. Again, thanks. After all, this is new physics.
Mass curves space, creating a gravitational well. To escape, a rocket must overcome this curvature.
In Einstein's theory, you need infinite mass. There's no such thing.
Mass curves space, creating a gravitational well. To escape, a rocket must overcome this curvature.
You've heard the story. Space is a stretchy fabric. Gravity bends it. Clocks slow down near massive stuff. Nothing outruns light. What if I told you that whole picture might be the wrong map for the right territory? Let's myth bust, then rebuild. Myth 1. Space is a rubber sheet that warps. In the quantum physics framework, space isn't a fabric at all. It's a zero-point low-density field in vacuum equilibrium, an expanse that stays balanced. No ripples that slow clocks, no sagging tarp. Just a field maintaining its calm baseline. Myth 2. Energy and mass are the same thing in motion, so engines gain mass as they speed up. Here, energy and mass are distinct. Energy is weightless. When I pour energy into thrust, I don't make the engine heavier. I make the ship faster and more momentum-rich. Manufacture mass is manufacture mass. Acceleration doesn't add pounds, it adds pace. Myth 3. The speed of light is an inviolable cosmic cap. In this view, c is a velocity, a property of how disturbances move through the field, not a universal speed limit posted on reality's highway. So what actually happens when I accelerate? If energy and acceleration have no fundamental ceiling, then continuous thrust stacks velocity without hitting a baked-in wall. Push long enough, steer cleanly enough, and in principle, faster-than-light travel isn't forbidden by the field. It's a reachable regime of motion. But what about GPS and time dilation? I'm told satellites tick differently, so time must slow. In this framework, clocks don't change their intrinsic rate. What I measure as timing offsets come from path lengths and differences in field density. Space near Earth is denser than deep space, and signals traverse those regions differently. So I correct for geometry and field conditions, not for slower mechanical time. Put it together. Space is an equilibrium field. Energy is weightless push. Mass is built, not grown by speed. C is a velocity, not a veto. And timekeeping quirks are environmental, not existential. Does this overthrow modern physics? Not today. It's a rival map, a way to ask sharper questions. If experiments keep matching its bets, linear thrust without hidden mass, signal behavior tied to field density, navigable superluminal corridors, then the map earns its mileage. Until then, I'm testing, measuring, and keeping my curiosity at full thrust.
And what else could we do? We can also unlock the secrets of the Big Bang. You see, Einstein's equations break down at the instant of the Big Bang and the center of a black hole. The two most interesting places in the universe are beyond our reach using Einstein's equations. We need a higher theory, and that's where string theory comes in. String theory takes you before the Big Bang, before Genesis itself. And what does string theory say? It says that there is a multiverse of universes. Where did the Big Bang come from? Well, Einstein's equations give us this compelling picture that we are like insects on a soap bubble, a gigantic soap bubble which is expanding, and we are trapped like flies on flypaper. We can't escape the soap bubble. And that's called the Big Bang theory. String theory says there should be other bubbles out there in a multiverse of bubbles. When two universes collide, it can form another universe. When a universe splits in half, it can create two universes, and that, we think, is the Big Bang. The Big Bang is caused either by the collision of universes or by the fissioning of universes. If there are other dimensions, if there are other universes, can we go between universes? Well, that, of course, is very hard. However, Alice in Wonderland gives us a possibility that maybe one day we might create a wormhole between universes. This is a wormhole. Think of taking a sheet of paper and putting two dots on it. The shortest distance between 2 points is a straight line. But if I can fold that sheet of paper, then perhaps I can create a shortcut through space and time, called a wormhole. This is a genuine solution of Einstein's equations. We can actually see this in string theory. The question is, how practical is it to go through one of these things? We don't know. In fact, there's a debate among physicists today. Stephen Hawking, many physicists are jumping into the game of trying to figure out whether it's physically possible to go all the way through a wormhole. Because if you could, then you might be able to use this as a time machine. Since string theory is a theory of everything, it's also a theory of time. And time machines are allowed in Einstein's equations, but to build one is extremely difficult. Far more energy is required than a simple DeLorean with plutonium. You know, trillions of years from now, the universe is going to get awfully cold. We think the universe is headed for a big freeze. All the stars will blink out. Stars will cease to twinkle. The universe will be so big, it'll be very cold. At that point, all intelligent life in the universe must die. The laws of physics are a death warrant to all intelligent life. There's only one way to escape the death of the universe, and that is leave the universe. We are now, of course, entering the realm of science fiction, but at least we now have equations, the equations of string theory, which will allow us to calculate if it is possible to go through a wormhole, to go to another universe where it's warmer, and perhaps we can start all over again.